I'll let you. Okay. As we promised you guys, we do have our expert, generator expert, Jerry Boggs here from Interstate Powers or Power Systems, and he will walk you guys through generators requirements and some EPA requirements. Um, so what I did, I already walked them through sizing a generator.
Okay.
From the other side.
The dark
So,
side.
so I don't know if we will go that far away or, but they already sized the generator.
Okay,
Just FYI. So I'll let you take it from there.
very
Thank you,
good.
Jerry.
Again, I just wanted to say hi again. I am here for you folks. I tend to run very, very informal presentations, so if you've got a question, just holler it out. Especially with a group this size, we're going to be real casual. So I've been in the business, just to give you a little background, all of my career, which has been, I was with Cummins, the dark side, so I do know a little bit about that software. But I was with Cummins for 35 years, and I've been with MTU, which is a new name of Detroit Diesel, for the past 10. So I've got an extensive background, and there's not too much I haven't seen in those years. We have some pretty wide territory, and we have about 18 generator sites in our territory that I'll show you in a second. But we have a lot of young folks in that group as well, and I've been kind of a mentor to a lot of them. So again, if you see something you really don't understand, holler. I can probably help walk you through it. We're going to cover a lot today. As Chad mentioned, we're going to, is this the place to, that arrow? Okay. I apologize. I got to change this slide and take out all of this stuff. But what we're going to cover today, and I'm throwing a little bit more in there even since you've seen it, Chad. We won't cover the sizing software since Chad's already done that for you. But I'll give you a brief introduction of our company, discuss the different product types that are out there, mainly the fuel types and that kind of thing, and why some of them are better than others for given applications. And there's been a lot of upgrades through the years of transfer equipment. We'll go through that. When I did a presentation for Mayo's people for Dunwoody, the business side of Dunwoody, I did some training at the Mayo Clinic, and it was very good to see the transfer equipment. I actually upgraded. I asked if I could upgrade their product, and they said, yeah. So that was a very good thing. When I did that training, we did a session like we're doing today, and then we went and looked at one of the facility people that was there, one of their operations. We took a bus ride and went and did some hands-on stuff, so that was a good addition to the transfer stuff. So we'll talk about different kinds of loads. You guys probably know more than I do on that one. Discussion of design types. We're going to look at two. The issues of today, and boy, it used to be a lot easier to sell generator sets, I'll tell you that, and you'll understand why when we get to the end. So that'll pretty much cover it for what we're going to go through today. Again, I'm here for you, so questions are welcome anytime. All right, who is Interstate? Interstate Company is the headquarters, is the parent company of Interstate Power Systems. They've been in business since 1958. They're located right down by the Mall of America, if you know where that is. We actually have, I say 9 states here. I'm covering one extra state, Missouri, in addition to those. I'm covering some different product, which I'm going to go through later. But typically, we've got 18 branches across these states, and we got St. Louis too down here for gas product, which I'm doing. But we're spread out fairly wide. And again, the headquarters is right here, Minneapolis. Product we carry, again, I said that MTU, On-Site Energy, you see the logo up there in the upper right corner. That's the new name of Detroit Diesel, relatively speaking. MTU stands for Motor Turbine Union. They're headquartered in Germany. And MTU on-site energy is owned from a factory standpoint by two groups, 50% equally. Those names you probably recognize, Daimler-Benz and Rolls-Royce. So we've got some very deep pockets at the factory level, well entrenched. Product line we're going to, and this is a picture of a 20-cylinder. This is a 3,250 kilowatt generator set. Just for a point of reference, that's about 4,500 horsepower to drive that. And we'll go through different types of products here in a minute on diesel and gas side. We do have a full generator product line. This is a shot of our test line, test cell down in Mankato that was just updated. As an operator, we're doing a lot of things totally by computer. Very, very nice facility now. We are a complete power systems manufacturer. Again, what that means is we sell the generator sets, gas and diesel, in a range from 30 kilowatts up to 3,250 right now. Automatic transfer switches from 40 amps up to 4,000 amps, including service entrance rated stuff. Switch gear, paralleling switch gear and distribution if we need it. And a full line of accessories. Those might be remote radiators, and now oxidation catalysts and all kinds of things like that. Battery chargers, vibration equipment, vibration isolators. On the natural gas side, LP gas, we have models, industrial models from 30 to 400 kilowatts. And this is standby stuff now. The GM engines are on 30 to 60 kilowatts. Ford engines on 80 to 125 kilowatts. And we use a Doosan engine from 150 to 400 kilowatts. On the diesel side, we have industrial models from 30 kilowatts to 3,250. On the small end, up to about 200 kilowatts, we have John Deere engines. And above that, we are exclusive MTU Detroit diesel engines. In addition to the standby product, this is product that I am introducing to our whole territory, personally. So I am my own department in this regard. I am introducing prime power generator sets that are gas powered. And these run up to 2,150 kilowatts. These are a tried and true product that's actually coming over from Europe, Germany specifically. And they've been sold in Europe and Asia for about 30 years already. But as we get into more and more stuff, and I'm going to talk a little bit about this at the end of the presentation today. There's a product out there, in addition to standby, it's prime power, but it's called combined heat and power. I don't know how much you know about that, but we'll throw in a little bit at the end. And combined heat and power is just a new name for cogeneration. So we'll discuss that near the end of the presentation as well. All right. Moving on. Any questions so far? Diesel sets. Here's that 3250 now sitting on a truck. Give you a little bit of an idea how big the thing is. It's probably around 30 feet long. This picture's kind of funny. We used to, right over here on where this black is, the driver actually got in the picture, and he had a little beer belly that was kind of sticking out under his shirt, so we took him out, photoshopped him. Here's a picture of a set being delivered. This is down at a facility in Minneapolis. Notice there's no signs on the building or anything. This is a very, very exclusive data center. They don't like to let people know where these types of operations are, but that's a 1,500 kilowatt set being delivered down there. Here's another data center that they told me not to say who it is, but this is 3M. It's in St. Paul. We had this when we had the Kohler line, and there's 3 900 kilowatt sets there. And the fun thing to point out in a system like this, there's a lot of redundancy built into systems like this. This is probably a very, very critical load that is way above what you're going to see in a lot of cases. There's actually 2 sets of oil filters on the thing. So if this system had to run for any duration of time, you could actually change oil while the thing was running by switching filters. So it's a pretty sophisticated system. No, 1 oil reservoirs, but 2 sets of filters that are switchable here. You can see them in the picture. Same thing on the fuel. 2 sets of fuel filters as well. Right. That's an either-or system. And the valving is right there. You can kind of see the handles. But very, very critical systems. This is another one that we did a while back. This is a super target store, and we're actually taking over the whole facility with that generator. So you'll see the utility transformer sitting out here and the CT cabinet, and we actually have switch gear underneath this wrapping here that'll get taken off in a little bit there. But we see these kinds of crane operations commonly. Here's another picture of a generator that goes outside. I'm thinking hang on just a minute. Yeah, we'll cover this again in a little bit here. But this is a unit that is what we call a skin type enclosure. A neat thing about this is it's totally self-contained. These little louvers up here, it's a good time to tell you about those are actually inlet louvers. It goes in, comes across the engine over this way. There's a radiator that sits about right here. And this last section here is actually an open duct, and that's where they direct the air up. This is a form of sound attenuation that we'll talk about in a little bit as well. But the bottom has a fuel tank in it, and we'll talk more about these as well. And that's actually a tank within a tank, dual contained fuel system. Control options that we have. NFPA 110 is probably a regulation you may or may not have heard of, and that applies to generator sets. It displays both the engine and generator operating parameters, AC voltages, kilowatts. We can do that by leg as well, and also all of the engine controls. So we can see oil pressure, water temperature, those kinds of things. We can communicate via an RS-485 port to our remote annunciator. Here's what the control looks like. This control is actually made by Basler, and if you're familiar with utility-grade relays at all, Basler is one of the manufacturers of industrial-grade utility relays, protective relays. A little bit about the control and what it does. I'm not going to go through those bullet by bullet for you. Just a little idea. And here we have what we call the RDP 110 remote annunciator. All generator sets typically today will have a remote annunciator, so you can immediately tell if there's an issue with the generator set. Even if you move the control on the generator to the off position for maintenance, do an oil change or whatever, you'll have an alarm that comes on this thing, so they know things are being worked on. And this is required by NFPA 110 applications, any legally required system. All right, fuel types. The main thing we'll talk about right now is natural gas. These again are in smaller sets, and I do have a few opinions that I'll share with you as we go through. But on the pro side of why we would use natural gas is there are no storage issues. We don't have to worry about filling a tank. We don't have any of that. It's lighter than air, so if there's ever a leak, it's going to go up, not down. Natural gas is readily available. It is very clean burning as opposed to the other fuels, and it can also have an automatic propane backup. And what that's for, it's kind of a pro-con situation that's on the con page. But you'd want an automatic propane backup if we had a seismic zone. California is a good instance. I spent some time in California and in the West Coast in general. I was in Washington and Oregon. And a lot of that area is seismic. The San Andreas fault runs from like San Francisco area all the way up into Washington. In Washington, it changes a little bit. It becomes a different type. But that fault runs right through Portland, Oregon as well. And engineers discovered a long time ago in an earthquake, you can rupture a natural gas line. And for an emergency generator, that's a bad thing. So they said, well, let's have an automatic propane backup. And we can actually switch these on the fly. So if there's ever a rupture, there's sensors that say, okay, shut the solenoid valve off for natural gas, turn on the propane, open that valve, and away it goes. It takes off again. Sometimes it can do it on the fly, sometimes it just restarts. So that's the automatic propane backup. On the con side of natural gas, it is probably the lowest BTU fuel, so it's got the lowest amount of energy, so we might derate that a little bit. And as I mentioned before, service interruption is possible, especially in the seismic zones. Propane, another gaseous fuel. Basically, there's no difference in the carburetor itself for natural gas or propane. So propane is also a very clean burning fuel as well, as far as the internal workings of the engines, the pistons, and all that stuff. It's clean burning. It stores well. It's available on demand. You can call your supplier and get it, if your tank is getting low and so on. It's got a higher BTU content. If you remember, natural gas was 1,000 BTU per cubic foot. This is 2.5 times more energy in the same volume. And it can be taken off as a liquid or gas. And I got a little story about our area specifically that I always like to bring up. And the instance is in North Dakota, not far off of I-90, and where the wind blows pretty good. That freeway does get shut down a lot, and it gets extremely cold. And what happens in rare instances, if we had a vapor takeoff only, we can get vapor and liquid out of the same tank, okay? It's just how we take the fuel off. So if we look at the liquid level in the tank, there's a vapor level above it. On those extremely cold days where the wind is whipping, if we had a vapor takeoff, we may or not be able to vaporize enough fuel to run that generator set. So what they do is they take it off as a liquid. This tank is pretty well pressurized. It's very heavily pressurized. So we'll take the liquid off and we'll run it through a vaporizer, an external vaporizer that we've got a water jacket heater on the engine already, so it starts quickly. All generator sets do, whether they're diesel or gas, to make sure they'll start in 10 seconds. So that engine's always warm. So we use a little heat exchanger and run this liquid fuel through a primary loop, and it actually gets vaporized by the heat of the water jacket. So then it's pressure reduced through regulators and so on, and then brought into the engine. And what that does for us is two things. If we had a vapor tank, there's two ways to fix that problem of not vaporizing enough fuel. We could oversize this tank to the point where it filled up most of the room, but we'd have enough vapor to run the generator set. That's not really a cost-effective solution. But if we take it off as a liquid and vaporize it, we can optimize the size of that fuel tank. We can get it as low as we want to. In a legally required system where we have an automatic backup, technically by the rule, we only have to have a 2-hour on-premise supply. So we can get this tank size down quite a bit. On the con side of propane, there are some. Propane is heavier than air, so it will settle in low areas uh, if there's a leak. When I first got to Oregon, I did a lot of work with the telephone companies. They wanted me to to go visit all their sites, and they said, you know, we're ashamed to admit it, but we don't really know what we've got in some of these sites. So I said, sure, let's go do it. So we actually went up and looked at all their stuff, and they told me a lot of stories on that trip. One of them was they have radio repeaters located on the top of mountaintops, and those would now be cell sites and things like that. So they still have this equipment sitting up on top of high hills. And they had one that they actually had a generator set inside the building, and it was propane. There was a leak, and this was back in the days when they had relays instead of solid state stuff. And it took that repeater site off the top of the mountain with an explosion. So nasty situation. So it is heavier than air, and I've told consultants for a lot of years now, don't put them inside. These are outside units only. So even we had a railroad company that came back with a story too, that they actually located the generator set in a low area, and they had a leak there, and it took it out, but nothing else. But they put it at the bottom of this little bowl type area. So they relocated and bought a new set. So it's heavier than air. That's very dangerous. Liquid takeoff requires a little more equipment. They've got vaporizers and things like that. So not much on the con side, but just have to watch it if it's going in someplace where you put it. Here's a sketch I did several years ago showing a typical gas system and what they look like on the engine. Got a manual shutoff valve. This is a dry fuel strainer. And there are particles that come through on the gas sometimes, and this little leg picks those up, and there's a plug on it. After you shut the valve off, you can do maintenance, pull that plug out, and drain any particulates that are in there. If you have mechanical contractors, they'll call that thing a dirt leg. So it's not as neat a name. Fuel strainer sounds better. Then comes into a primary regulator. Typically, most like a residence or something, typically, and small business, is going to have like a 2 psi inlet. Maybe Dunwoody would have the same size here if they're running furnaces or something. 2 psi is very common. And the outlet pressure is between 7 and 11 inches of water. Okay, anything that's connected to the engine has a chunk of flex in it someplace because the engine rocks. So that gives it a little bit of a flexibility there, so it can rock and start up and so on. But the solenoid valve, once the transfer switch, and we'll get into this again when we cover that, sees that there's an outage, one of the first things that happens is that the engine will get a start signal, and it'll open this solenoid valve at the same time. So it's letting that 7 to 11 inches of fuel pressure in. And then a secondary regulator mounted on the engine knocks it down a little further in the outs range, and then it goes into the engine.
Why carbureted? Why not use like an injector, like you'd see on a normal diesel?
This is not a diesel. This is gas.
Oh,
this is natural gas. Yeah. So we've got spark ignition here. Good question. Also, the secondary regulator, there's one little difference between natural gas and propane vapor, is this regulator might be mounted upside down with the propane. And I'm not exactly sure why, but I just know that's what we have to do. Fuel considerations for diesels. On the positive side, it's got a very high BTU fuel content. I think it's in like 40,000 per gallon or something like that. Low volatility. Won't see a lot of fires with diesel floor. It might get real slippery, but with a diesel fuel leak, I should say. And it's readily available from suppliers. On the con side, there could be some storage. The storage does require some maintenance attention. If you don't use all the fuel, you might need that fuel clean because you're going to get a bio thing happening in the tank where things are going to start to grow over time if it sits too long. And I'm talking over a year's time. Also on the con side is storage requires dual containment with alarms. You folks may or may not be able to remember maybe 10 years ago, you drive by gas stations, you'd see backhoes doing stuff with the tanks, taking the tanks out and so on. Well, that's kind of what started this. What was happening was we had electrolysis acting on the skin of a single wall tank, a tank that was buried. When I mentioned the phone companies in Oregon, they got a lot of mountains, and I put a lot of fuel tanks up in the mountains that were advertising 20-year guarantees and so on. But they were all single wall. And over time, electrolysis would act on the skin of those iron tanks, and it would actually corrode those tanks. It took a long time, but it actually had a small amount of current that was corrosive. And that was true of the gas stations, too. So the EPA got involved, and they said, okay, well, when we bury a tank, we're going to do it a little more safe. And there was different ways to do it. You could put a containment vault in there, and what they would do is they'd make a concrete area, a tank, if you would, maybe fill it with some gravel, and then set the single wall tank in there, and then cover that up with gravel. And that was one way to contain it, so if there were ever a leak, it wouldn't go into the soil. It wouldn't hit the concrete. Well, generator sets do that too, but what they do is they put a tank within a tank, but they're two sheet metal boxes. And we put a float switch down in the corner to detect if there's ever a leak of that tank that's sitting inside the other tank. And if you think about it, that'll never happen, because if it's got a good weld that's survived, the soil isn't covering it, so there's going to be no electrolysis. So it's kind of an overkill for a fix, but
You just have to use like a water fuel separator then when it's above ground like that, or something.
that's a good point. We do use a lot of water filter separators right on the engine, and they've got a drain on the back. If you remember that slide, back here, these are actually water filter separators here, and they do have a drain right on the bottom there, so it's a good way to get rid of that.
You said you guys use that to like mount stuff underneath. Does that kind of make that a little more complicated when you have to use a back mounts to keep it from vibrating a lot with that tank right underneath it?
Another good question. There is isolation between the generator set and the skid that it's mounted on, and we'll cover that in a little bit here. There's some other things that we'll talk about. Did a good segue because it's coming right up. Other common options. Generator enclosures. I kind of touched on this a little bit already. This is an MTU weather enclosure. This is kind of real basic. If you look at this, you notice there's no louvers on it. These are service access doors. There's two more on the other side. So service guys like this because they can get right in there and do their thing, and it's easily accessible. I talked a little bit about it earlier, but again, this enclosure has an inlet louver on the end down here and an outlet over here. The fan on an engine generator set is different than it is on your car. And how it's different is in a car, the radiator sits here, the fan is just inside that, and then you have the engine, right? Well, the engine comes in across the radiator through that fan, which is sucking it in across the engine. It hits the firewall and goes underneath the car, and that's how the engine is cooled. Well, you don't have any motion with a generator that's just sitting there, standing there. So they reverse the fan, and it's a pusher type fan. So if it's sitting here, this fan is pushing out this way. That creates a negative pressure inside the enclosure, so it sucks in the air from wherever. That makes it real flexible where to put the inlet louvers, too, as we'll see in another second. Here's a little different design. If you remember, I talked a little bit about sound attenuation in an earlier slide. This is another type of sound attenuation. It's just minimal. It's like a step above the weather enclosure. So we call it the weather enclosure with the exhaust sound scoop. That's this part here. The other one I showed you, it just finished off the whole thing, and you had a longer tank, and it was more aesthetically pleasing, but we'll save a little sheet metal by doing it this way, and just use the up duct, direct the air up. That's going to reduce the noise, because noise travels in a straight line. Okay? So this is a little bit of sound attenuation. And this one we got the muffler on top, whereas the other one you see here, we mounted it inside, and all we had was a little rain cap poking out of the roof. And the inlet would be over here. And again, this is a dual contained tank like I described. So this is a tank within a tank. And it's got a little step there because these tanks can get kind of high at times. So it gets you up to the control. That's what the step looks like. No magic. And again, here's that sound attenuation version again. Taken from a slightly different angle, and there's just enough to where you can see how that doesn't go straight in there? There's a little baffle there that's directing the air up and over and then around inside here. Again, noise travels in a straight line. It doesn't care whether it's an air inlet or not. So this little baffle deflects the noise back into the enclosure. And anytime you turn the noise, you reduce it. So a lot of thought had gone into that. And again, this is the one that does have an internal plenum in here where the air is coming out and going up. So the radiator is about here. Again, the dual contained tank, a little smaller, not quite as high, so it doesn't have the step. Here's another method of sound attenuation. This one is a very clean design. Again, no louvers on it or anything. So we've got an inlet and an outlet. And you can tell the inlet always because it's coming in from underneath. This is open. So it's sucking direct down over the engine, out and up. So a larger version of the inlet and the outlet. This time we're attenuating the inlet this way. Still another way to do it. This one is up at Northtown, if you know where that is. There's actually some pieces that they use on the inside of buildings called sound attenuators. And they have a bunch of punched holes in them, and they just disrupt the sound waves. They're very effective. But this enclosure houses a 1,500 kilowatt set. And these attenuating modules are located behind these louvers. Just a different way to do it. Same idea. This one is out at a hospital in Hutchinson. Also, one thing you'll see that's handy to do on a diesel set is trailer mounter sets. And where you see these a lot are in municipalities, cities, especially where you have public works people, sewage lift stations in residential areas. So those might have different voltages. So a couple things that are done with generators going into neighborhoods. Number one, we're putting on super quiet housings like we just talked about. But the other thing we can do is we can make different voltages, because these lift stations might be 120, 208, three-phase over here. This one might be 277, 480. Maybe we want to be able to take it to the well, so that'll probably be at 480 with a reduced voltage transformer on it, right by the water tower. Or maybe we even have something in the garage and that's single phase. So we put a switch on a trailer mounted set that allows us to change voltages just by flipping the switch. We drag it to when there's an outage and the lift stations need to be pumped down. You just set it on the voltage we're going to first, pump that lift station down, then drag it to the next one, turn the voltage over to 480 or whatever we need, and keep going. It's a very handy thing for a utility to have.
So you basically put just different transformers in there, and it'll just...
No transformer. That's a good question. Do I have a yeah, I do. Okay. This is a challenge for me.
Maybe I should get you.
Here, I'll do it over here for now. We have 6 coils on the generator set. Most modern generators today. Let's do it this way. We'll do 6 coils. 1. They call them 12-lead generator sets. That's the ones I'm mostly familiar with. There's some 10s and some others. And then we'll do this. If you look at this and you say, okay, every one of these has these 6 coils that we're going to wind inside the generator in. Right now, I'm kind of showing that in the delta configuration. I'll draw a line in a second. But there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These 12 leads will be brought out to the output box. And in the case of that trailer mounted set, that's actually going to be brought to the voltage change switch. So it's a pretty hairy switch. This one is about this long. I designed that whole end on that thing that you're looking at. But in this configuration, we would tie these together. This is kind of an odd voltage, but the one I've drawn here, this is 240 volt, 3-phase. This is 120, 240, 3-phase. And these two would actually be tied together. These two, or these two.
Change the amount of windings and change the voltage of outlet.
Huh?
You just change the amount of windings on each side to change the voltage.
To change the, what we do is we change these connections. Okay? So this would be, we'll call this leg 1, leg 2, and this is leg 3. In this configuration, there's a nasty thing that happens. So this is actually neutral down here. So in a 120, 240, 3-phase system, figure these, in this configuration, let's say the coils had 120 volts. Okay? So between leg 1 and neutral, these two, we got 120 volts. Same on this side, so that's 120 volts. That means we have between leg 2 and leg 1, we've got our 240. This up here, because we can't get to neutral real easy, this is what they call a wild leg. So in most operations, most cities that use this, it's not real effective anymore. So 120, 240, 3-phase is kind of going away, and they're using 120, 208 in its place. So this is the only one that has a wild leg. Because it's approximately 208 volts line to neutral. Because it's going from neutral here to that vector. So they don't use that too much anymore. But it illustrates how the coils are used pretty well. The other configuration on the switch I see why you want me to use that thing.
You can use it if you want to just switch it up.
No, that's all right. On a Y configuration, take those same coils. Here's 1, 2. We'll call that the neutral point in the middle now. And we'll come out 1, 2, 1, 2. There's 2 legs there that are tied together. And here we have L1, L2, and L3. That makes sense? And neutral in the middle. We usually ground. So there we've got, it's much more usable in a neighborhood where they use 12208 most often I've seen is in low-rise office complexes. Very, very common. So these 2 leads are tied together here, there, and there. And between any leg, which is neutral in line 1, 120, neutral line 3, 120. And actually, that's actually, this is what they call a high Y. You actually have these coils parallel to the low Y. So I do that a little wrong. So right now, between line 1 and neutral, you'll have 277. And between line and line, you'll have 480. For what I've drawn. 277 is a very common industrial lighting voltage used in warehouses and stuff. But that's the difference. They call this a high Y, and again, doing it this way, paralleling the coils like that with a low Y configuration around the horn. And then you'd have like your 120, we'll call that line 2, line 1, line 3, 120 line to neutral. Any line to line, you'd have 208. That's how they do it without a transformer.
So basically, when you're flipping those switches, it's actually moving like
These contacts,
something.
totally reconfiguring these contacts.
That's cool.
It is very, very complicated, and those switches are expensive because they have lots of contacts in them. And they have to be able to carry the current for line voltage, too. So,
So Jerry, then you can get, like if it's a Y, you will get 208, 120, and 480, 277. You can't get 240, 120 out of the same, or can they?
240, 120,
3 phase.
not in the Y
Okay,
configuration.
so it's, you have
Only a delta.
limitation on what you can get out of that. Like it's 240, 120, 240, 277, or 120, 208. That's a lot.
I'll give you a little thing that I've used over the years. One of the old buggers that mentored me told me, he says, you know, if you can divide the high side and the low side voltage by 120 evenly, it's a delta configuration. If you can't, it's a Y. Real simple thing, but it's true. 120, 240, 3 phase, that was the first one I
Yep.
drew. That's a delta. An odd one that I just went to earlier this week. One of the guys took me out to a site because he wanted me to look at it. And it is a trailer set that we're having to build. I thought for a minute, and I've seen, like, I told him I've seen 3 of these in my career, which is close to 40 years or a little over 40 years. But it's a 240, 480 delta. Again, both divisible by 120, so it works. It is a delta configuration. But it's not a parallel delta, like technically the one I showed you earlier was really a 240, 480, because it had 2 coils in series. But it's a parallel set of coils for 120, 240, and the bottom one is the center tap for the 120. No, you can do it. But I thought I was going to be buying a transformer for this one. I studied what I saw when I was at the site. There was a little diagram. And they had like a little link bar here for each leg. Yeah, this is a neutral, and then there was a ground over here. But here, the way it was shown on this sheet, I thought they were showing something to the neutral. It was like 240. I thought I was seeing that here. I just glanced at it and I told the other guy, take a picture of that so I have it. But what it was actually showing was In either configuration, it was 480 or 240 for this particular setup of the bars that they had on this unit. So it was actually a 277, 480 set, which is much more common. I didn't know that until we got back to the office. Studied that diagram. And I've only seen 240, 480 three phases in my career. That tells you how common they are. Not. Good question, though.
Thank you, Jim.
You bet. Water jacket heaters. So I mentioned earlier, all these things have to start in 10 seconds. And that comes out of the NFPA 110. And what that means is the power not only, the generator set only not has to start, but it's got to transfer over and be on emergency in 10 seconds. So it's imperative that they're kept warm, and they're kept warm all the time, even in the summer months. Here's another one. This is a little something you might put on your car. This is if you want to keep your car warm in the wintertime, just a 120 plug, and this one's commonly called a tank heater by other people. Battery chargers, again, if it's just sitting there, you've got a standby unit, and it's connected to the battery, that battery will decay over time. So this battery charger just keeps a little bump on the engine battery to make sure it's there when you need it the most. So all emergency systems have a battery charger. Vibration isolation. Back to see the one that questioned? Isolators. There's lots of different kinds. Show you a few of the more common. This is a good illustration if you look at one like that. That kind of looks like an engine mount, huh? And there's a good reason for that. It's basically the same thing. You see them more like this. They're squished and kind of flat a little bit. But these will be mounted between the engine and the skid. And it takes a lot of the vibration out, especially when it's just running. Starting, you're going to see it rocking a little bit. But these are neoprene, and they have enough give in them to where they rock. Well, that makes sense on engines that are relatively small. On bigger sets, like a 2 meg set that might be, or the big one that I showed you in that picture, that 3250, those are solid. I mean, they weld everything right to that skid, so it's all one piece, if you will. In that case, we go to an isolator like this. It's a spring isolator. And you see some of these have little stuff on the side here. These are adjustment screws for the side of this. This is actually a seismic isolator here. And there's adjustments you can do for those, for seismic areas. So a lot of different kinds. And we had some small air-cooled units that we used to put up on these mountaintop sites when we only had like 15 kilowatts or so. And we used to call this waffle pad, because it's got cork in the middle and neoprene on both sides, and it's kind of a rough fit. But it worked really well for those types of sets, and we just run some of that stuff underneath the skid of the generator set, and then we bolt through it to keep the generator from running around. Keep it in place. All right, I've run through generator sets. Any other questions that you have on generator sets? I covered a lot quickly. All right, this is a definition that I came up with a long time ago when I've been teaching other guys. An automatic transfer switch, what is it? It's a device used to safely transfer power to the load between two different sources. And we're going to look at this. I have a story. I'm going to jump ahead here a little bit. You'll get guys that think if you look at it, this utility power here and the load, this might, just consider this for a second, it's just coming straight in, and we don't have this out here. They say, well, I can just take a plug off down in my building distribution and plug the generator in there and operate anything in the house that way. And that works fine until the power comes back on. If he hasn't switched his main off to keep it contained, the generator backfeed into that box, he's in trouble. So a transfer switch will safely, if you look at this drawing, safely disconnect, because when this thing operates, it's going to move this arm from here over to this position, totally leaving just a dot there as far as the drawing is concerned for utility power. So if utility power comes back, that's all the further it's going is to the contacts. And the generator set is feeding the load fat, dumb, and happy. All right. Go back one here. All right. I'm going to talk about the transfer switches in their order of complexity and why they were formulated in the first place. The first one is the most cost effective, which is a nice word for it's the cheapest. But it does the job just fine. It's the most common type because it is most cost effective. But the downside is you will see a blink in the lights. Here's why. Before I move on, though, I'm going to describe, there's 4 time delays in every transfer switch. And I'll describe what they're for. This drawing is a good one to do it on. There's 4 time delays in every switch of every type that I'm going to show you. The reason they exist, if we take a day like today, Minnesota, we've just had some ice and we've just had some snow. That might be on the power lines outside. Some smaller towns out down distribution ways. Okay. Now we got a tree that's sitting close to that power line, and that might be just bumping it enough to be causing a problem with power someplace, and then it's just blinking off and on. Well, the first time delay is a time delay on start, and it's only for like 2 seconds to make sure the power is really out. Because on a larger set where you have that instance I just talked about, you don't want to be slamming that big diesel starter on a 20-cylinder unit home every 2 seconds. So if it's gone for 2 seconds, we say it's real. Start the generator, and then the signal goes in. That's the first time delay on start. The second one is used on non-legally required systems only. It's a time delay on transfer. So in other words, the sensors in this switch have seen utility power is gone on this terminal. It's the control of the transfer switch that tells the generator, hey, start. So it goes out and it signals the generator, and this is done through the contacts and the control in the switch, which operates all the time whether there's power or not. So the generator set starts, comes up to speed and frequency, and the second time delay, like I said, is a time delay on transfer. And what it's for is just give the generator set a little time to run and stabilize before we transfer it from this position over to generator, before we hit it with a load, basically. So that's what that's for. But if you remember, I said this is a non-legally required system. A legally required system has to start and be online supplying power to the load in 10 seconds. So this one is not used a lot. But for homeowners, it's fine. Okay, it's not legally required.
Harder on the equipment then? We have to take an exchange of that work.
It's really not. It's not too bad, I don't think. Again, the engine's warm already from the water jacket heater, and that's the thing that's really that you're really concerned about. So I question the validity of even having the thing, you know. Don't really need it. The third time delay, okay, we've been running on generator power now for several hours. Power comes back on. Transfer switch will see it in the voltage sensors over here on the utility side. So now what it's going to do is we have a time delay on retransfer. Why? Give you an instance. Instead of the cold, let's talk the heat in the summertime. Hot day in the summertime. Everybody has turned their air conditioning on. Okay? Over a course of time. people were all different, you know, they come on gradually, this house, and half hour later this house, and businesses, you know, they've turned up their thermostats and got the air conditioning running. Okay, now we've got all this air conditioning load on. It's an extremely hot day. What's the utility trying to do when we first retransfer back off? When the utility first comes back, if you imagine the control room, now the utility is trying to start all of these air conditioning systems online at the same time. You guys know enough about motor starting right now. You've been through the sizing program. What can you tell me about the starting of a motor? One motor. It's going to take between 7 and 10 times rated running current to get that motor running, right? And more importantly, if you look at the power factor of that motor, it's going to take a lot of kW, or real power, horsepower, to do it. So even with the utility trying to start hospital chillers, residential air conditioning, RTUs, and low-rise complex, all at the same time, it may or may not do it. So the utility might go right back down again. Well, you really don't want to be switching back and forth, transferring power between utility and generator set all the time. So they say, okay, on this time delay, let's make it about 30 minutes. And we typically, our technicians will set these at about 15 minutes in the field, realistically. And it's waiting to make sure that utility is really back for good. So it's not going to be going off again. So that's a time delay on retransfer. And then finally, once we've transferred back, now we've gone from generator back over to utility, the generator's still running. Most modern engines today on generator sets are being squeezed for every ounce of horsepower they can get. So in part of doing that, you're going to see a lot of turbochargers on these engines, gas and diesel, both. So these turbochargers run really hot, and they run directly proportional in temperature to the amount of load that's on them. So if we've been running in a building now off of this transfer switch, and that generator set has been operating near its capacity, it's pretty hot. And more importantly, the turbocharger on that thing is really hot. So if we switch it back over to the utility, we've now gone from full load on the generator to no load. That exhaust temperature correlates. So the exhaust temperature comes down pretty quick. So they use that cooler, relatively cooler air to run through that turbocharger to cool it down gradually, because they're really expensive. So that's a time delay on stop. A lot of customers will call, and that's typically about a 10-minute is what our technicians set them for. They can be a little longer, but 10 minutes you're going to be running. Huh? Yes, most modern turbochargers are oil cooled as well. So this gives the whole turbocharger unit a little bit of chance to cool down with the lower exhaust temperature, the blades and everything.
Do you guys typically use like a dual bearing, or are you just mostly single bearing?
I haven't gotten into the inside of the turbo,
Okay.
but I'm pretty sure they're at least dual bearing. Yeah. So that's the final time delay, is time delay stop. So time delay start, make sure it's a real outage. Time delay transfer, if we can, with a non-emergency or non-legally required transfer switch. Give the engine a little time to stabilize before we hit it with a load. Time delay on retransfer to make sure the utility is really there for good for the duration. And time delay stop, so that engine has cooled its turbocharger down. All the transfer switches we'll be going through have those same 4 time delays in there. And some of them got a little more sophisticated and put more in for other things, but those are the basic 4 that you'll always see. Okay, getting back to the open transition. Going back to things that we say, this is the most cost-effective type. It's the most common as well because of the cost effectiveness, and we will see a blink in the lights. The reason is say we're obviously going to see it in a power failure. It's more than a blink, it's dark. So, but now take the instance where we're over on the generator set and the utility comes back. Okay, now we've got two live sources. So what we're going to see when we have passed our time delay on retransfer, we're going back to utility now. We flip this, but as it's transferring, it's not a lot of time. It's going to take about 100 milliseconds to get from this position over to this position. During that time, you will see a noticeable blink in the lights because you're in an open transition mode. Okay. Moving on. Here's what a picture of that switch might look like. It's just a plain box. The inside, you can see the three pieces. This is the front of the control that's actually shown here. That we're seeing the backside here. Here's the actual control itself where we can do some adjustments on those time delays I was talking about. And this is the actual contactor that will bring the conductors in to wire to. This bundle of wires here has those voltage sensors that are watching all the terminals to make sure, okay, especially utility terminal, is power gone, start the generator set, so the control will handle that. Also, you'll see over here, these are LEDs, these four things here. And this will tell you, I don't know why they say it like this. Other suppliers say source available, but this is source accepted. And they have, in most cases, if it's all is well, you'll see the normal light lit, and it's typically green. Emergency is typically red on the LEDs. So if we have both sources running, both these will be lit, green and red respectively. Transfer switch position, again, the same colors. When you walk by the transfer switch normally, you've got normal connected to the load. Both of these will be green. Exercise, these will be changing around. So we see the transfer switch in the normal position, green. When it transfers over to the generator, you'll see the transfer switch position for emergency light up red. Okay, moving on. Another type of transfer switch that you're going to see is what they call a closed transition switch. This is more expensive than the open transition, simply because it's a little more sophisticated. Going back, looking at this, these are my drawings, but a lot of engineers use the same type of drawing. When it flops between utility power and generator power, I call this point here for the load the pivot point. So this is what's pivoting, is this point, and that's the load. In the closed transition, what we're doing is we're actually picking up another pivot point. So this one pivots between connected and open. Same thing here, connected and open. But I've got two pivot points, one here and one here. And building load is connected to that. So a closed transition switch is more expensive. It could require utility protective relay. In most instances, it does. Most utilities do. But they're getting a little more lax on this. Excel typically says, okay, you got to have an ANSI 32R, reverse power relay, in there. And right now they're requiring an 86A and a 62PL, which is a parallel limit. Can only be, if you're parallel to the utility for longer than 100 milliseconds, you get an alarm. So it's sophisticated relaying that's very expensive because it's looking at some very finite periods of time. Closed transition is not for all types of loads. UPS systems aren't a good one for this one because they might do some wild things. There's no blink in the lights. A good application for a closed transition switch is, if you think about it, warehouse lighting. It's a dumb load, but if it's an, the high discharge type that takes a long time to restrike, so that's a good application for this type of a switch. Again, it has 2 pivot points. What I've shown here in this sketch is that 100 milliseconds of time when they're both, the load is closed to both sources. So utility is there, generator is here. Both sources are closed. But they figure for 100 milliseconds you can't hurt too much, and then it opens. So we're going over to generator now. This is going to open in 100 milliseconds, so only the generator will be feeding power to the building load. That's the concept. Getting a little more complex. Maybe I told you warehouse lighting would be a good one for the close transition. But the generator set's going to see a heck of a, it's going to see full load instantaneously on any time we have a close transition. So bypass isolation has a different requirement and a different reason. It uses an automatic transfer switch contactor and a manual switch contactor, both connected to the same load. I'll tell you right now that anytime you double the amount of contactors in a transfer switch, the price is going to go up. Very true. You've also spent more money to wire it that way and on the wire itself. So it's going to be more expensive than conventional switches. The main reason for a bypass isolation transfer switch is it's used where manual intervention, in other words, you got an operator there, will allow functioning of the emergency system. When I explain, it'll make more sense. We'll look at the drawing. Okay. This came out of California, and it was 4 hospitals where they had an issue where a patient died. Very serious situation. He was on the operating table. What happened was they had a malfunction in the automatic transfer switch, which is this one, this contactor. You'll see in this situation the 2 sets of contactors, one here, one here. The issue they had was this switch malfunctioned and they could not get the generator power through the contactors to supply the load. Patient died. Big deal. So, code was reworked, and we had to, in certain cases, supply bypass isolation transfer switches. Again, we parallel sets of contactors. If there's a problem, this one can actually be racked out. Let's look at how we're supplying load here. Normal power here comes into the switch, goes this way through the automatic transfer switch to the load this way. Okay. This set of contactors, the manual contactor is set up the same way. It's actually supplying load power to the load through its contactor, but this one has to be manually operated. So there's a problem with this transfer switch. It can actually be taken out. Now we're dealing only with a manual switch. Normal power was coming in here to the load. Now we got an operator that can go out to that switch. He's already taken the automatic switch, or no, he's left it there. He might rack it out and get it away from this thing. So now he's taking the manual switch and he's changing it from normal and closing this switch to the generator right here. So a generator can supply power now up through this manual switch to the load. And it doesn't require a lot of time, but it does require a manual operation. Here's what they actually look like. Again, you've got rails down here on the bottom. This is the automatic transfer switch contactor here. This is the operational arm for the manual transfer switch. So you rotate that to operate the switch manually. This is the crank out here to actually rack it out and get it out of the operation. And you can see from the physical size, it's big. This is a 90-inch cabinet. There's another set of contactors that you don't see that are in the back here that are being operated again by that handle. Bypass isolation transfer switch. One last type that I include in the presentation is what we call a soft load transfer pair. It is an automatic transfer switch, but instead of a contactor, we're actually going to use two breakers that act as a switch. The operation of this switch is transparent to the load, which I'll explain why in a minute. It's very user-friendly in utility curtailment programs, and I'll tell you a little bit about what those are. Got a factory out here. I don't care. Pick a factory. We're running the whole factory on a generator set in backup power. Well, we'll take the store, the Target store that we saw in the thing. That's using a switch like this. Well, the utilities like those, and customers like those, because when they operate, the load doesn't know anything happened, but I'll show that in a minute. Utility curtailment programs are set up to where there's an arrangement with the utility company. They come to the Target store and they say, look, you guys run that generator when we tell you to run it. It's usually on a hot day or a real cold day when they need more power. And we'll give you a 20% reduction in your power bill all year long. Good deal for the customer. He's just reduced his power bill by 20%. And typically, this curtailment period is going to happen only on hot days. Average has been 6 or 7 times in a summer, in a hot summer, when they've actually done that. So it's a good deal for the customer for this program, because he gets a lower power bill all year long. It's a good deal for the utility, because he's getting a pretty good chunk of power, maybe a megawatt even, in one spot, and he doesn't have to buy more expensive power from Canada, wheel it down and pay everybody who owns the lines and everything all the way down. That gets expensive. So the utility wins. I win because I sell this stuff. So I'm a happy guy. So we had a really good program there. And we'll get more into it in a little bit. I'll show you some language, but that's what a curtailment program is. And requires utility approval, obviously, because we're paralleling with their equipment. They want to know anytime that they've got a live source on there, because they might be trying to fix a power failure, and they got a lineman up there working on the pole. So they have to know about it, and we have to have protective relaying in place for safety. And it's the most expensive design. Here's what it looks like. And here's what happens. It's got utility power coming in here, going through a generator main. And this is all in one box, by the way. 3 sets of contacts. Utility power coming in, supplying power to this bus that the building load is connected to. So it goes right into the building. Okay, now we've got our generator sitting out there near the transformer. Utility calls and they say, run your generator set. So we start the generator setup, and we have paralleling controls in this box that looks at the utility. And it adjusts through the governing system and the fuel to match the frequency. So we're in sync with the utility. And we have controls in there to automatically adjust the amplitude of the voltage so we can match the utility voltage. So we've matched the speed and the frequency. We're synchronized with the utility. We close that breaker. We're now supplying with the utility the load, the building load. So the store is running along. It hasn't seen anything happen because all we've done is close this breaker. But it's in sync Now we open this breaker and we're still supplying power to the load by the generator. The load doesn't know anything happened. It's a great system. The utility says, okay, we're going to run it for about 6 hours. At that time, they bring power back to this point. Same thing happens. Sensors in here look at the generator power versus what the utility is doing now. Synchronizes, matches speed and voltage, closes the utility breaker. Load is ramped off the generator back onto the utility. Load still doesn't know anything happened. It hasn't seen an outage. So it's a user-friendly piece because IT people aren't screaming you, hey, we lost power, because they've not seen an outage. So it's a really sophisticated way to transfer power and also help out the utility. Load curtailment programs. This is what one particular set of transfer pairs that I've used in the past looks like. And here we have the two breakers, utility main, generator main. This is a utility grade protective relaying here. Happens to be a Schweitzer 451. And they've gotten very sophisticated. They actually have a PLC built into them. So we can do all of the logic for a transfer switch within the protective relay, which is pretty cool. Here again is what it looks like sitting out in the parking lot. You wouldn't really notice anything different or sophisticated there. But again, the transformers over here, this is just a transition cabinet being fed into the switch. And of course, the generator is coming underneath here and hitting the generator terminals. Very clean operation, no difference on the inside of the store at all. Typically, you want to do these when the store is being built if you can. All right, we've gone through transfer switches. You got any questions? Again, went through it.
Joey, do you take a 5-minute break?
We can take a 5-minute break. You have a question back here?
Just while we take a break or whatever, is there any way that you could maybe draw out on the board a little bit what the connections and everything like that when you're talking about that soft transfer and everything? Still a little confused about how exactly, because I know that you have to, if you're running at the same time as utility, your generator obviously has to be running at the exact same frequency.
Correct.
But like almost like it's almost like parallel between the two or something like that.
That's exactly the word to use. It is parallel.
But then it causes it to automatically, because I know like when you have those power plants or something like that, it's the fact that they're all sort of like tied together that you told us you're spinning at the same frequency, sort of. I don't know, that explain it very easily, but there's a way that you like kind of sort of draw it up on the board or something, how they do that. The connection from the south.
Okay, yeah.
You know, when we went to the Cummins power generation in the spring, and they were showing us how they can boot up the generators and say, hey, we want this percentage of the building's power running off the generators, and we'll pull this much from the utility and whatever. They can sit there and move it up and down.
It can. There's a device in there. The same device is built by Woodward. It's called, let's see, AGLC, Automatic Generator Loading Control. It's a piece of electronics that revolutionized this type of control. I actually used to demonstrate that here at the Cummins factory years ago when it was first installed. And I just demonstrated the system before that as well. But the way they're set up, we'll look at a couple situations here. We'll put 3 generators in this. They've got 5 up there. And we'll throw a utility main out here. That could actually be the generator. And we'll make this utility here. And we'll put the load here. So basically, what we're doing, it's all done, there's not a lot to draw. It's all done electronically, like I said, with the loading control that's in. We'll call this part here the paralleling gear. As you saw in the back room behind the conference room was here, then they had the control room with all the breakers and stuff. And then you walk through a door and you go into the room where the generators are. Well, all of the magic is happening here. In those gray boxes, they had the protective relaying and everything. That generator loading control is actually in each cabinet, each paralleling switchgear cabinet for these sets. Now, they do a lot on the sets themselves too, in the control that's out on the unit. But what we're trying to do, each set will match its own speed and frequency to this breaker, because this is the point of closure onto that common bus. The load, typically when the system's not running, we've got this breaker closed, the utility main is closed to the building load, and the generator main is open. This is normally open. So that's how it works. Now there's a lot of schemes for equipment because we've got a generator main. Hospitals do. You know, hospitals aren't a good example because they have transfer switches usually. But there might be a situation where we have a load that's grown over time, a factory, and we have multiple sets. So this load has grown over time to where it's more than the capacity of a single set. So now we're going to require at least 2 generators to be on this bus before we close this breaker. Because this load is going to kill one set, right? So those types of things are developed in the controls. So we have to have at least, that's just a programming requirement we put into the control. Okay, we got to run it because now we got to have 2 sets on before we close this main. So that's the requirement that we developed over time. Also, another thing, 3 generator sets. Gunderson Lutheran Hospital down in La Crosse was owned at that time by a bunch of doctors and people with money. But it's a very large operation now, and they're very sophisticated. But they were going to be doing some expansion. They had 2 generator sets that my company actually built for them from scratch back in the 70s. And they said, we need more capacity here, but we're going to be building a huge physical complex in a couple of years. We don't want to have a new system. And I tried selling them 3 new sets and paralleling gear. They said, no, we're not going to do it. There are other things that you have to be concerned about, just other than voltage and frequency and paralleling systems. And I knew it because the reason I was trying to get away from it, these things were old. These generator ends were built by electric machinery down in Minneapolis years ago. So I knew where they were, so I went down and I said, hey, here's what I got. This is the model that I bought. This is all the stuff on it. They looked at me and said, we don't do that anymore. Okay. So I went and I had to source a different generator and then wound up actually Leroy Somaire built one for me. So I could build, well, what I told people I was doing, I'm building a brand new 30-year-old set. But I was doing it to match the pitch, and that has to do with how the generator is actually wound inside. Remember I told you there was like 12 leads and stuff. Well, this one had kind of a weird one. But I matched it as close as I could to what they had there. I wasn't exact though. And that pitch has a difference, and it's in a percentage. These were like, I want to say 70% pitch. The common today is 66. When they call that 2/3 pitch, it's a percentage. And the reason they do that percentage today, just about everybody does it, is it does some neat things with nonlinear loads and with harmonics. That's it. But when you have differing pitches on the generator sets, a little bit, you'll actually have a small amount of current that circulates this way between those sets. You know, in this case, both sets, because it's on a common bus. So there's just a little bit of current there, and there's things you can do to keep that current down. Like, if you wanted to spend a lot of money, you could do some studies, and you actually would put in a little inductor in series here to help eliminate some of that stuff. But you will get circulating currents, and I told the hospital, you're going to see something there. Sure enough, we got down the road, we started that generator set, put it online. Just a little bit of current showing. It's not usable, it's not doing anything, but it's there. It's just because it's circulating. So that's the other thing. Does that help with what I've shown here?
Yeah, for the most part. I guess this can probably go back to the basic electrical knowledge that had slipped out of my mind from like first year, but like when you're paralleling utility, as far as I'm assuming the generators are putting out power in 3-phase and the utility is 3-phase. So how exactly, I mean, are the generators when they fire up and you're paralleling the utility, how do they sync up like?
Good question. Good question. Okay.
What's the word? Like frequency-wise, how do you get them in sync?
All right. That's a good question.
Now, Brian works for himself, just for the record here, Fred.
That's okay. There's no real magic here.
Which was what, Brian? That's what he's looking for, Jerry. That sine wave.
That's the sine wave. Okay. All happens here.
All the magic happen in the sine wave.
120 degrees. All right. What's happening? That's a 3-phase sine wave. Let's call this 3 different units. How we're shifting and getting the phase angle down to 0 here, okay, is with speed. Okay, that's actually coming out of the governor control. So that's actually taking and bumping, it's giving what they call a bias signal to the governor. And it's going to bump it for a while, and you'll gradually see these moving closer. And if you're looking at sync lights, you'd see the sync lights actually darkening. Because the more spread out we are, the more of a difference we have there, the brighter the lights are going to be, the sync lights. So as that bias signal comes out of the governor control, that's going to bump them into sync. Okay. Now, the other thing that's happening at the same time is the amplitude. This is done by the voltage regulator. It has to be a special regulator that is a paralleling regulator. What it's doing is saying, okay, what's my utility amplitude? At the same time, we're bumping it with the governor to knock it into sync. The amplitude's being adjusted to match the utility. Okay? Those two things happen, and when we get it down to the single sine wave, we close it to that breaker. We close the generator breaker to the utility. And at that point, nothing can change it. Because we aren't going to change the utility with the generator set. We will be in sync. It's physically impossible to get help unless we open the breaker. That help?
Yeah.
You went all the way to the signal, huh?
Huh?
You went all the way to the signal instead.
There you go.
Do you want 5 minutes to recoup?
Yeah, yeah.
Okay, we'll get you there. You guys take 5 minutes and we'll continue. I know you need to print, so don't worry about your printing. If you want to send, you ready to send the printers?
You can set it.
Well, they'll join us here too. So we'll get you money. We ready?
Yeah.
Okay. All right. We move into a discussion on nonlinear loads. There's some opinions here in this particular slide. The first one being the main one. Nonlinear loads need diesel engines. This came out of a period of time in my career back when nonlinear loads were first being introduced. It has to do with how a diesel engine reacts to a load versus how a natural gas engine reacts to a load. Diesels tend to be more stiff, and natural gas tend to be more soft. So we see more transitional things happening with natural gas, and there were a lot of issues with running nonlinear loads at first. They've kind of gone away as the industry has progressed. I call that kind of a system problem. In other words, nonlinear load was running fine and the diesel engine generator is running fine, or the natural gas engine generator was running fine. But when we switched the two online together, there were issues between the two. So those have kind of gone away since the advent and the perfection of nonlinear systems. They do need special consideration in sizing because of the heating of the neutral. So that's mainly a little bit of oversizing that software programs now take care of. Examples of nonlinear loads: UPS systems, battery chargers, VFD drives, T8 lighting ballasts, and I'm sure you can come up with a few others. Nonlinear effects can be offset with other loads. The nonlinear effects that I saw from a generator perspective were mainly notching on the AC wave. And we could reduce those notching effects by adding more linear load or incandescent lighting type things. Mm-hmm. Okay. All right, first one that I'm going to talk about is an uninterruptible power system, or UPS, very common today. And this is used to maintain power to a critical load, typically in IT information technology centers. The guy that's running the computer operation for a company. And they are never to lose power. And this is typically done in a data center that's backing up extremely critical loads for factories, for financial operations, those kinds of things. Basically, they operate with three basic pieces. Very simple to explain this way. First part is a battery charger. You notice the AC wave coming in. Any battery charger is going to take AC and rectify it to DC to charge batteries, shown here in this part of it. Second part is the batteries themselves. The third part is an inverter. Okay, the inverter is connected to the batteries, and its job is to change DC back to AC. So now we've got an AC out of this device, and that in turn is powering our critical load. So if you think about it, if we were to lose power out here, this power would still be there because the inverter is still connected to the batteries, and up until a second ago, the batteries were still being charged by the charger. So now we're dependent, however, on the life of the batteries to keep producing this waveform through the inverter to the critical load. The power comes back, this waveform is restored, and again we'll immediately start to recharge the batteries again.
What's the life cycle of a battery like? Like how much charge time do you usually have?
That's the golden question. And telephone companies have been the user of this type of systems for many, many years. So what you'll see when you go to the local telephone office, which is a great illustration for that question, is you'll see racks of batteries. And these are typically NiCad batteries that they were using. And all you do to lengthen the time is add more batteries. It's just that simple. So the more batteries you have, the longer time you have. And that's true of a small UPS system that you'll buy from a Liebert or PowerWare or people like that. If you want 30 minutes of time, you're going to pay a lot more money for the batteries than you are if you only need 11 minutes of time, we'll say. So
basically, most of it's just going to be enough time for them to see whatever they're doing and then be done with it.
yep. What IT people call that is we want enough time to do an orderly shutdown. So typically that's how the batteries are sized. But more batteries equals more time. It's just that simple. Other motor loads that are out there, air conditioners or RTUs. RTUs, if you're not familiar, is rooftop units. It's a smaller air conditioner for a specific area. Chillers, you'll see these in bigger buildings. Again, doing the same function. Typically see those a lot in the hospitals. Elevators, obviously, those are pressurization and exhaust fans, circuit pumps, fire pumps. Fire pumps have some critical, you probably learned a little bit about that in your sizing program. You got a 15% voltage dip on fire pumps.
It will be next project. They're doing
Okay.
commercial now.
Okay,
It will be in the spring project.
all right. Lighting loads. We talked a little bit about discharge and when we were talking about closed transition transfer switches. That's a good application, discharge lighting. Anything that needs a restrike time, if we can hit it with something that doesn't interrupt the power, all the better.
Terry, how's the LEDs doing in terms of effect on the generators? All these LED lights.
I honestly don't know. That's still new enough to where,
Not a big deal yet.
no.
Because they're just like any other line. They're taking AC to DC.
Mm-hmm. All right. Two basic building designs. We're going to look at sticking this in a building now. We'll look at doing a partial building, which is basically only the critical load and some additional loads that are picked up by the generator set. And then we'll look at doing the entire building. The facilities run entirely by the gen set. In the partial building, you'll see a lot of my sketches are included in this particular one line. We look at this. We'll take it from the position of going through the utility all the way to the critical load here. So up here we have utility power coming in. Here's the transformer that comes in through an entrance rated fuse disconnect or whatever, some kind of service entrance device into the main distribution panel. We've already done a sizing of how big our critical load and other stuff we're running is here. So that is taken off and fed to a transfer switch that is watching utility power right here. We have our automatic transfer switch. We'll see that this is an open transition design. And we got our generator set here. Our transfer switch feeds our critical load. Notice that, well, critical load and other load. The very critical load is out here on the end, on the other side of our UPS system. But notice in the actual emergency distribution panel that the generator is running, also has some lighting in it. It's also got the air conditioner, the rooftop unit for the IT area, we'll say, included. And we left a spare breaker in there because we didn't trust the IT guy. He's going to put something else on there. So that's kind of the way it's set up. Again, we do have a UPS out here covering the extreme critical load in this case. So what happens now? The power fails. This is gone. The sensors here on the transfer switch see that. And at this time, this is gone here. This whole panel is dark because the power failed. But the critical load is still being powered out here because the inverter section of the UPS is still connected to the batteries. This sine wave is still there. Now, since it's gone here, the generator set is told to start, comes up to speed and frequency. Sensors here see it, transfer over to the generator set, and now we've repowered the battery charger down here on the UPS. So this is still totally operational. The UPS load, the critical load, has not been without power. And because we've designed a system like this, where the generator is now feeding and recharging batteries as well here, because this critical load is still being fed, we call that a ride-through because of the UPS. The UPS gives us a ride-through between the utility failure and the supply by the generator set. It's carrying the load at that time, so it's riding it through. At the same time we're recharging the batteries in the UPS, we've also fired up some emergency lights, so the lights in our room are still working, and the air conditioning is still there. So it's a hot day outside, so the air conditioner is still running for the IT department. So it covers our critical load on that way, in that way. Utility power comes back, the reverse is true. Voltage sensors again here, we'll see it. They'll start going through its time delays, and we'll go through a time delay on retransfer. Again, we're going to make sure that the utility is really back. It's a hot day, and we want to wait for maybe 15 minutes to make sure that, yes, it's really, really back and it's powering all the loads out there. That happens, it transfers back. Generator cools down on the 4th time delay that it sees, and then finally shuts down, and we're back the way we were before. And then the next instance is the entire building design, and we've actually already talked about it a little bit. But it's just like that Target Superstore we saw the picture of. We had the transformer there, utility main. If we want to curtail, the power company calls, says, run your generator, comes up to speed and frequency. We parallel, match the voltage, match the frequency, close the breaker, open the utility main. Load doesn't know anything happened. Reverse is true when utility comes back here, sensors see it, tell the generator to synchronize. The generator control then is in sync with the utility. It closes the utility main. Signal is then given to do the shutdown sequence for the generator, the cool down, and so on. Again, opening that breaker, cooling the generator down, shutting it down. Load doesn't know anything happened. That's the entire facility. It's a lot cleaner for others, for outside. Okay, we've talked about generators, transfer switches, types of loads. Other considerations that are out there are some codes. This one's getting a little dated. It's been around for a while. UL 2200. It was established in 1998. And this has changes that pertain mainly to the manufacturers of gensets. Caterpillar, Cummins, MGU, everybody out there. And it's how they're shipped from the factory. It's for stationary applications only. 600 volts or less, doesn't apply to medium voltage. Open or enclosed units the same. Any fuel. And changes to multi-voltage block heaters, battery boots, ground straps on the alternator. Has a lot of changes. Other things that we've been talking about in some of the sound attenuation housing designs are noise. I'll give you a little bit more to look at here. Many municipalities have noise ordinances, and to date they've been putting them on their websites. You might have to call and find out where exactly they put them. They put them in different places, but one thing about noise ordinances, they're usually enforced only when there's a complaint. Then they'll drag the book out and see if there's, how high is it, and noise travels in a straight line. It can be attenuated in several ways. We've looked at a couple different designs. We know that if we turn it, if we can turn the noise, it quiets it and attenuates it. And it will continue to be a concern in the future, as long as we have an EPA. The noise reduction may be required by city code, it usually is. And for whatever reason, they've chosen 7 meters or 23 feet as their distance that they want to start measuring at. And a good specification will require that a noise reduction must be quantified. In other words, let's talk about 70 dBA at 23 feet, and then everybody should know what's being discussed. Reducing noise does cost money, big money. A few rules of thumb for noise. Doubling the distance from the source is the sound is reduced by 6 dBA. So a generator running at 80 dBA will have a noise level of 74, approximately 50 feet away, if we started at 23 feet, approximately. Two equal sound sources will increase the overall sound by only 3 dBA. So 2 80s makes 83. And to the human ear, for dBA, twice the loudness is a 10 dB increase. I always throw in a couple of fun things I've accumulated. This one did come from Cummins years ago. It has mosquito in flight. I kind of like that one. You know, it's 10 dBA. Falling feather is 0. Thinking is 0. On the other end, a jet engine's 130. Volcanic eruption is about the same. So fun things to look at. All right. One of the bigger changes that I've been involved with also is emissions. They've kind of made me at Interstate the emissions guy. And I've thrown a few more slides in at the very end that I had mentioned earlier that I'll go through. But a lot of terms have cropped up over time, and you've seen them popping up here. It used to be a lot easier to sell generator sets. Let's just say it that way. We're going to be talking about some definition changes as of, I'm going to say 2011. And the ones we're going to be looking at mainly are emergency standby power and non-emergency power. Non-emergency and emergency. 2011 was when the next escalation of EPA requirements happened for compression ignition internal combustion. Compression ignition is diesel when you see that. It's CI. The other thing you'll see is SI, and that's spark ignited, and that's gas sets. Just that simple. So the two definitions, non-emergency and emergency, that I've come up with states emergency engine generators that only operate when normal power is lost or required for testing and maintenance. This does apply also to pumps, engines that are driving pumps. So if there's a flood someplace, they can run that engine. That's an emergency as well. Non-emergency applies to anything that is not emergency. So all else. Examples of non-emergency are peak shaving, utility program, which is the curtailment program I described that was a good deal for customers and me and for utilities. So that's now classified as non-emergency. Why did they make this distinction in definitions of emergency and non-emergency? Because they're going to change the emission requirements immediately of those two. And here it says, I highlighted this, again, this is emergency stationary internal combustion engine means any engine whose operation is limited to emergency situations, like we just described. And the pumps are brought in here. That's the way it's worded. Compliance requirements. Okay, now that we've defined it, what are the requirements? Okay, emergency generators may be operated for the purpose of maintenance checks or readiness tested, or in our case, in the facility we're going to design commercially, exercise period for the generator set. Okay, those maintenance checks, blah, 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 are limited to 100 hours per year for an emergency generator. Okay, and if owners don't like that, they can petition for a change. But there's no time limit on the use of emergency generators in true emergencies. So good. Anytime the power fails, and you can run it. There's no limit on those hours.
So Jerry, if you have a data center, you lost the power, you call your data center, would that qualify as an emergency?
Yes.
Oh, it's not just emergency, but cool, yeah. It's not emergency light or emergency elevators or, you know, emergency fire pumps or really.
This is coming out of the air quality group of the EPA. Bear that in mind. So this generator set for that data center, if the power fails, that's an emergency generator set.
You run the whole data center on.
Correct.
Just don't-
By this definition. If the power has failed, it's emergency.
It's not bad.
No, it's not bad. What does this mean for our engines? I'm speaking as a Detroit guy now. No modifications are necessary on our engines. Current product line will remain the same through 2014, and that date is in there because there's changes that are mandated in 2015. And we don't have to worry about doing any exhaust after treatment. So they give us a table, and horsepower over here is not really engine horsepower. It's the metric equivalent of kW. Or I'm sorry, the other way around. kW here is the metric kW, equivalent of horsepower. So, and you can see the timeline up on the top, and we're out here now. So, and again, we're meeting all of those requirements right now with our current product line. So, no changes, no big deal. But that's purely emergency. Now, same definition. This time I've highlighted the other thing that kind of bothers me. Okay, I've discussed the curtailment programs that the utility company out there. It's a good deal for everybody, but now the EPA has said that stationary compression ignition internal combustion engines used to supply power to an electric grid, or that might supply power as part of a financial arrangement, in other words, the discount to the customer from the utility, with another entity, are not considered to be emergency engines. So this part of the regulation is shooting down the curtailment programs that the utilities offer. They're saying that's not emergency. So why are they making that point? Because there's going to be different emissions requirements. You can still do the program with the utility, but you've got to bring your existing generator set or new generator set, if that's what you're designing for, up to a new emission standard. Exhaust after treatment will be required. A NOx catalyst strategy on new engines. Minor modifications to the current engine platform are needed. And it must be supplied as a package from the factory. That's really not true anymore. and I should take that line out. There's the two ways we can address this issue. We can either have a factory certified engine on new equipment, or we can have the EPA will also recognize a third-party vendor, and they'll call that, if they can get the emissions in line, and it has to be tested, they'll offer what they call EPA compliant. So factory certified by the manufacturer or EPA compliant by a third-party vendor. And here's the emission requirements for those. Pretty much across the board right now, it's got to be at least a Tier 4I if it's new equipment coming out of a manufacturer. Engine companies, MTU, Cummins, Caterpillar, have a few engines only at this period in time that are factory certified. There are a number of manufacturers scrambling to cover compliant engines so new equipment can meet this. Why? Because nobody has really gone into the changes that are required in 2015 yet. The transition year is coming up starting next month, and you can see that there are some requirements. Tier 4, purple is Tier 4 final. So this is as stringent as the emissions are going to get. So in a little stronger language in the last session that I did, that I tried to restrain myself a little bit here since I'm on YouTube. What will these changes require? Let's look at some of the stuff. Basically, guys, an SCR is something that takes the NOx, the nitrous oxides, out of the exhaust stream. There are things engine manufacturers have done in meeting all the tier levels prior to 4, and they've done a good job in reductions. I've got another slide that shows, it's a good graphic that shows how it's been reduced. Tier 4I is also going to require some particulate reduction. But basically what we're doing, we're taking that exhaust stream out of the engine, and that's exhaust gas with the oxides of nitrogen shown in red here. We're adding something called urea. It's a powder, and it comes into the exhaust stream. We'll show you how it's injected into the exhaust stream and reacts with the NOx that's coming through here. And that urea does change to ammonia and steam in that process, and that whole conglomeration is then run through this catalyst, which is actually a catalytic converter, if you will. And it comes out as water and nitrogen out of the exhaust, finally. The main thing, the SCR in this case is not a silicon-controlled rectifier like we in the electrical might think. It's selective catalytic reduction. This targets NOx only, the SCR does. And it's reduced by reacting it with another chemical, a reducing agent. Most commonly it's urea, a liquefied urea. And that can reliably achieve a 90% reduction in the NOx, but it's very expensive to add that stuff.
They use like an afterburner for those two then, in the catalyst?
They use a, yes, and we'll kind of look at that in a section. They inject it right into the exhaust stream.
Yeah, just kind of a portion of the exhaust stream injected back in.
Mm-hmm. And the SCR systems can operate over a temperature range of about 600 to 980. Here's what it looks like in a little graphic way. Taking the raw gas here, adding the ammonia or urea, same stuff, with oxygen, running it through the catalyst, and getting nitrogen and water out.
Days of the college when you have to balance the chemical equations and everything done in college.
Yep.
Balancing chemical equations.
Mm-hmm. The nuts and bolts, what does it look like? Well, there's a lot of extra pieces that go in here. To your point about afterburning. Well, it's kind of like an afterburner right here. Um, this is the urea container. It's controlled and shot in to a mixing section here that gives an exhaust outlet afterwards that's a lot cleaner. But all of these controls have to be added and piped to be injected along with the air. This is the air compressor down here, which is sent to the dosing box. So we're doing air and the urea mixture then through here with the exhaust gas that's coming out of the engine right there. This is where all the reaction is taking place, and the housing of the SCR catalyst itself to finish the process. Another peek at the components there. The mixing tube. Another thing about the urea, again with Minnesota and North Dakota and our neck of the woods, guess what? The best solution is a 35%, 32.5% solution, liquefied, that starts to crystallize at about 15 degrees. So we've got to do some heat tracing to keep our components warm, here in this area anyway. So we've got a little extra problem with the weather. Here's what they look like when they're totally installed. I think some of these are California installations. Here's a graphic I put in on this one too. It shows the amount of reduction. What we're looking at out here is 10 grams per kilowatt hour of NOx, nitrous oxide. So prior to any tier changes on engines, any cleaning of engines, if you will, by the EPA, this is what we're looking at. This is the 10 grams per NOx per kilowatt hour per hour now, and 0.6 of a gram per kilowatt hour of particulate matter is the other dimension on this graph. Tier 1 is the green box. Okay, and then over time, if you remember my graphic of improved emissions, we moved in 2006 to 2010 to a Tier 2 engine, which is the blue area here. Tier 4 interim reduces down to this box that's orange and the dark blue, and the final in 2015 is down here under 0.67, down from 9 point something grams per brake or per kilowatt hour. So this little box is where we're going in 2015. To do that total reduction has been very, very, very expensive. But it's a good graphic to illustrate that point. After treatment component costs, that's a little summary of what we'll need for NOx. Genset costs is the other thing we're going to need is a larger cooling system, revised genset design with the accessories, the SCR. We also got to look at the back pressure. You know, what are these components going to do to back pressure on the engine? So it's probably going to be larger piping on the outlets and so on.
No derating of the engine.
Hmm?
No derating the TW of the engine.
Possibly some, but that all has to be considered now in doing a generator sizing. Larger enclosures. Now we got a bunch more stuff. If we're going to be having an outside unit, now we got to fit the SCRs and all those components in the box as well. So a lot of things related are going to drive the cost up. Other related emissions issues of today. I threw these in here. Doing a little work here. I love this slide, so I had to put it in. I use this in my emissions presentations. What I've been talking about so far was tier level changes for new equipment. I've also been dubbed the Rice-Nishap guy for interstate, so that's a new thing for the EPA for existing equipment. People that have a generator set already and have had all these phone companies that were out there, all these factories that have done over time, all the people who've been enjoying that curtailment program, they get, even though they have existing equipment, now they have to spend more money as well, because that rule does apply to existing equipment. So
So they have to meet.
they have to meet new emissions requirements, but it's not as stringent as new engines. Okay.
Retroactive.
Retroactive, they're grandfathering this. What does RICE-NESHAP stand for? Reciprocating Internal Combustion Engines, National Emission Standards for Hazardous Air Pollutants. And I'm throwing this part in just so you, just a couple slides so you know about it. It's nothing that you have to worry about because this is existing stuff. But be aware that the EPA is active in many areas. The birth of NESHAP came out of the Clean Air Act, basically. And 6 criteria pollutants they're mainly concerned with is ozone, nitrous oxides, and so on, particulate matters, CO, and PM. And I've kind of split it off in this slide I made up just to show RICE-NESHAP is only targeting CO. And it's doing that because it's the next largest pollutant next to NOx. So new equipment is more concerned with this stuff, the reduction of this stuff. Existing equipment is mainly concerned with CO, and that's CO is being addressed by basically a catalytic converter on existing equipment.
Is that just the on for diesel?
Yes.
Okay.
This, what I'm showing you so far is diesel
Yeah.
with the NOx. The existing equipment does apply to spark ignited sets. So we're putting a catalytic converter on them as well.
They use a filter like on the very back end of the.
Yep, I've got us. You're doing a good segue for me here. The diesel oxidation catalyst is what they put on, and this is the main component for this. It's like a catalytic converter for your car. This is what they look like. So basically, we want to put these before we do the muffler. And I'm doing combination units, basically, which are the catalyst and the muffler all in one piece, just to keep me from putting too much back pressure on the engine, especially on existing stuff that might have a little wear over time. But this is what they look like. The catalyst comes out in this drawer out here. You pull it out. And I'm going to be talking customers that I've sold these systems to into putting one on the shelf. So as they do become plugged or need cleaning, they can pull their shelf off, put it in there, and they're right back in business. The other thing they're doing in this program is remember how a lot of engines had a blow-by hose that had little oil vapor coming out? We're catching that now, and they're calling that closing the crankcase. So that is coming out. We're taking it off here where this used to be a hose that would go down and they'd secretly get it a little bit away from the engine, but you'd always see a little oil puddle at the end of it. So now we're catching that. We're running it through a filter here, and then we're redirecting the air back into the turbocharger. And what it filters out and drains comes through this blue hose, and we run that back into the base of the engine.
How much blow-by are they getting?
It varies by engine, but some engines you'll see a pretty good puddle at the bottom of them, so you know that they've either been operating for a long time like that, but typically it's a drip. You know, you will get, if you actually took that hose and put it in your hand, you'll have a few drops in your hand before too long.
Yeah. So with these, because most of these are turbocharged,
Mm-hmm.
are they just running like a single set, like cam, so it's not dual cams, single load for it done, or are they running like dual cam systems on there just for the speed of the engine? Or?
If you have, no, typically we're seeing a single cam system, but it doesn't really matter. We can tee these things. I'll go back to the other picture. We can actually tee, you know, take the different outlets off the engine, tee it in and run it into the filter that way. And then we put it back into the, after the air cleaner, here's the air cleaner. After the air cleaner and before the turbo, is where we put the outlet of this filter, and it goes through. And again, the drain goes back into the tank. And that's my session for today. That last bit on the Rice knee shaft came out of this Code of Federal Regulations. Any other questions?
You guys change the RPM on, or is it pretty constant for those?
On generators, it's always 1800 to get the frequency. Yeah.
And then when you do like the close transition for it, then do you have to use kind of like a clutch in order to kind of catch it slowly so it doesn't like torque the engine real hard? Or
No, it's going to torque.
just let her buck? And
Yeah, let her buck.
That's awesome. And for sharing, guys, I know it's a long, great presentation. A lot more than you probably need for this project. I just want to remind you guys, everything that Jake said, you will be doing in the spring project. So all the panel switch here, all the generators. Next project will have 2 generators, something like 2.25 megawatt when you panel them for 4,000 amp switch gear. So we'll be using all this information for next project. This project, we did the 500 amp 28120 main panel, and we backed it up with the generator. And we use an auto transfer switch at the main. So
Okay.
just auto transfer switch, transfer the whole building.
Okay.
Close to 500 amp auto transfer switch. That's how we did this project. So.
Okay.
Any comments, any questions, guys? Do you have any question about this ruler, sizing it? I don't know if you want to run them through that one, or you guys, is it self-explanatory?
That's pretty
Yeah,
self-explanatory.
so how to use that one to size generators, and if you have any question, I can also help you with it. Yeah.
Okay.
Well, thank you, I appreciate it, thanks.
Thank you. If you have a question after I'm gone, my card's in the information that I gave you. Feel free to call me or send me an email. We have a full staff here too that can help route questions through. Be happy to help with anything that you need.